we've just seen that the expected value of a random variable that has a binomial distribution with parameters n and p is just n times p. Sometimes when we draw from the box little n times, we're not going to get any tickets labeled 1. Sometimes we're going to get one ticket labeled 1. Sometimes we're going to get 17. Sometimes we're going to get n. Right? On average, how many tickets labeled 1 do we get when we draw little n times from the box? On average, we get n times p. That might not be an integer, right? It might not be a possible number of tickets. It's on average what would happen in the long run. We all together? Okay, I asserted without proof that it doesn't make any difference whether you draw with replacement or without replacement. The expected value is still the number of draws times the average of the numbers on the tickets in the box. Okay? We have another random variable that's like drawing without replacement from this box of tickets. What distribution is that? If I draw little n times without replacement from a box of 0, from a 0, 1 box. Hypergeometric. Okay. So for hypergeometric, I would call this number G. Right? G is the number of tickets in the box that are labeled 1. There's n tickets in the box in all. Okay. What is the average of the labels on the tickets in the box here? It's still P, but I can write this in terms of the parameters of the hypergeometric. What's the fraction in terms of G and N? What is P? Yeah. Number of tickets labeled 1 divided by the total number of tickets there are. Okay. So let's suppose that I draw at random without replacement little n times from this box and add the numbers on the tickets that I see. That's like counting how many 1s I get. Right? How many tickets labeled 1 do I get in that sample without replacement? What's the expected value of that sum? Yeah, it would be little n times big G over big N, provided little n is less than big N. Can't pull more tickets out of the box than there are in the box if you're sampling without replacement. If I wanted to do that from the definition of the expected value, what would I have to calculate? So suppose I have a hypergeometric distribution with parameters n, g, and little n. Then how would I calculate its expected value if I didn't know this shortcut? Yeah, I'd be doing some sum that involves taking j times the probability that the random variable is equal to j. What's the probability that the random variable is equal to j? We have this sort of max and min thing. We have to worry about the possible values. But for a feasible term, what does it look like? From the good tickets, I need to choose j. From the tickets labeled 0, I need to choose n minus j. And from all the tickets, I need to choose n. Right? So I would be looking at the sum of j times this thing, this combinatorial ratio thing, and adding the terms for all the possible values of j. Possible values of j are going to depend on how many tickets I pull out of the box, et cetera. It's going to be integers, but it might not start at 0, depending on the sample size. Okay, so this mess is going to end up reducing to little n times big G over big N. which is the analog of little n times little p for the binomial. The expected value for the binomial is the same as the expected value for the hypergeometric. It is the number of draws times the fraction of ones there are in the box.